And this is the same thing of the drawing that we saw in the beginning. And again, let's just start at the compressor. All right. We're a gas when we come in there, and we're going to pressurize that gas. As we pressurize it, we're going to be high pressure, high temperature gas. I think what I'm going to do is take this particular slide because I like it so much. It kind of breaks everything down to, when is it a gas, when is it a liquid. As we look at the drawing, any of those lines that are thicker, those are going to be gas lines. Any of the lines that are skinny, those are going to be liquid lines. So the compressor, we come out of there, it's high temperature, high pressure, and it's a gas. It goes through our coils. We discharge the heat, we convert to a liquid. We're still high pressure. Our temperature is dropped, so we're medium temperature, and we're a liquid, so roughly about 100 degrees. As we go through our metering device, we're going to drop our pressure. When we drop our pressure, we drop our temperature. And that's going to also be a liquid. It's going to remain a liquid. So low temperature, low pressure, liquid, roughly about 20 degrees. We're going to pass it through our indoor coil. We're going to absorb heat from the inside. As we're absorbing heat, we're going to change from a liquid to a gas. So we're going to go ahead and expel gas from the coil. It goes in as a liquid, comes out as a gas. So as it comes out as a gas, it's going to be still low pressure. It is going to be a gas, and it's going to be roughly that medium temperature again. So low pressure, here it's saying low temperature, but roughly 50 degrees, and it's still going to be a gas. We go into our compressor, we pressurize it, we heat it up again, and the cycle keeps going on and on. If you look at this kind of carefully, you'll see that compressor, and I'm not talking about the fans that go ahead and blow the air over the coils. The compressor is really the only moving part of the air conditioner. So as I'm adding pressure into the system, I'm also releasing pressure at that metering device. And those things are supposed to be in tune perfectly. So when the system is fully up and running, as I continuously add pressure to the system, the metering device is continuously releasing the same amount of refrigerant so that I could get that equilibrium of pressures, and I can go ahead and make that I'm forgetting my word here, going from a liquid to a gas or gas to a liquid. My change of state is what I was looking for. All right, we kind of talked about this on some of our field trainings, and I just want to go a little bit more about some of the terms and things that we use. The first one is the term ton. Whenever we deal with air conditioning systems, we call them a 1-ton unit or a 2-ton unit or 2.5 tons, wherever it comes in there, but the term ton. I'd like you to know where it came from. This is kind of a test question that I've heard of as well, so I'd like you to be aware of it. 12,000 BTUs equals 1 ton, for air conditioning. And how they determine that is if they had 1 ton of solid ice, it takes 12,000 BTUs to convert that 1 ton of ice into a liquid. So again, we're changing state, going from a solid to a liquid this time, and it takes 12,000 BTUs to go ahead and melt 1 ton of ice. Hence the term ton. So when we look at house systems, we kind of want to get a rough idea if the system is acceptable or not, or if it's too big or too small when it comes with it. The term that the HVAC contractors are going to use is something called a J calculation. And at that point in time, they're going to be using the location of the home, and they talk about how many heat days we have. They're going to look at the amount of insulation, the square footage of the home, how many windows there are. Basically, what they're going to try and determine is how much heat loss is going to be happening in this house so that they could go ahead and put the right size systems to go ahead and replace that heat loss or heat gain. When we're talking about air conditioning, the houses are going to gain heat. We need to absorb that heat and remove it from the house. All right. So this is just a rule of thumb. This isn't something to hang your hat on or a hill to die on at all. It's just a rule of thumb. In our area, and I would say it's more to about 1,000 square feet per ton, that's a pretty decent rule of thumb. The more efficient a home is, the smaller the air conditioning we need to be. Nowadays, we're putting all this foam and everything else into the houses. We really don't need that big of air conditioning systems because we're not going to have as much heat getting through that foam and heating up the house, so we don't have to remove the heat as fast as when the older homes had very little insulation, drafty windows. All that heat gain was coming into the house, and we just had to remove a lot more heat, so we needed bigger air conditioning systems. All right. So a decent rule of thumb is about 1 ton for every 1,000 square feet. You really don't see too many systems smaller than 2 or 2.5 tons. Most of the ones we're going to run into, the smaller homes, are going to be about 2.5 tons. In my house, I do not have a big home. We have a 2-zone system, so they don't really run all that much. It's roughly about 1,500 square feet, and I have 2 separate zones, and they're both 2.5 tons. So we don't divide everything up when we're doing it and saying, well, wait a minute, you got 5 tons now for a 1,500 square foot home. What I do know is that for the most part, my second floor air conditioning and heating system is going to be running in the summertime more. Heat is going to rise. I have an open staircase. So that's the one that's going to be doing most of the work. The first floor one would hardly run at all. But it did. If the heat does come in there, it does actually run. All right. What we don't want to see, though, is big air conditioning systems on small homes, because when the bigger the air conditioning systems, they're able to remove heat extremely fast. Now, just getting rid of the heat doesn't always make us comfortable. All right, if it's hot and wet or humid, that's actually uncomfortable. I should say cold and humid is uncomfortable. All right, it gets to be clammy. So when air conditioning systems are also running, they're going to also be removing the humidity that's in the air as well, so we can make it cool and dry. The ultimate goal of an air conditioning system, when it's properly sized, is that the air conditioning system should pretty much run 24 hours a day on those temperatures at around 100 to 110 degrees in our area. And as it's running, it's constantly removing the heat that's coming in there. It's constantly removing the humidity that's coming into the house. It's giving you a comfortable, cool, and dry. Now, that doesn't mean that it won't shut off here and there, but for the most part, it's going to turn on and stay on. Going back to my house, when I have a 2-zone system, my upper floor one, in the hottest days of the year, that should be running pretty much consistently. And then rarely should the first floor go ahead and kick on. So the problem with large air conditioning systems is, A, they cycle on and off very quickly, and that shortens the lifespan. So the more they turn on and off, the shorter the lifespan is going to be on these things. And the second problem is going to be that they'll remove the heat extremely fast, but they don't remove the humidity, so we're left with cool and clammy air inside the house. This here is a common test that you could do. Those simple turkey thermometers or a dial thermometer. They work tremendously. All right. So we're looking, and I want you to remember these numbers: 15 to 20 degrees. That's our typical temperature drop. I normally don't take temperature readings on the filter side of the fan. I kind of just look at the thermostat when I lower the thermostat to see what the temperature is, because that's the same temperature of the air that's going to be coming through it. But I do take the temperature above the plenum up there, and I'll usually either remove the humidifier and get access to that area. I'll look for gaps in the ductwork itself that comes in there, and if I can't, I'll find the closest radiator. For those of you that decide that you're going to want to work with the thermal imaging camera, they're actually pretty cool. You just walk right by the registers, and you can go ahead and get a reading of whatever the temperature is that's coming out of there. What you don't want to do with those things is shine it on the ductwork. and take your temperature reading that way. The ductwork is never going to be the same temperature as whatever the airflow is, all right? So you want to get the temperature of the airflow, and that's where those turkey thermometers just make life a lot easier. So we're looking for it to be somewhere around 50 to 55 degrees. Supply temperature is typically 55 to 60. It's saying that temperature because it's using the return as saying that that's 75 degrees. But I don't know, I find that most people keep it somewhere around 70 degrees. So whatever temperature it is coming in, we're looking for 15 to 20 degrees of a drop going out. Testing air conditioners. This is a big one. All right, most home inspectors will use the temperature of 65 degrees, and I'll be honest with you. A lot of air conditioning systems can go all the way down to 50 degrees, and they'll run just fine. All right. We'll talk about heat pumps and what's the difference between an air conditioning system and a heat pump in a little bit. But heat pumps can run all the way down to 35 degrees, and they'll be able to work just fine. All right. But for us, being cautious, we're going to use the temperature of 65 degrees, and we kind of stick to that if it's been that temperature within the last 24 hours. All right. Now, the reasoning why we don't want to test air conditioners at a lower temperature, I need you to go back to your memories a little bit when I showed that compressor out there earlier. An air compressor can only compress air. All right. If I try to push liquid through that air compressor, then all I'm going to damage that air compressor, plain and simple. So you might go to a house, you're inspecting the home, and then you look at the air conditioner, and it might be just fine. But you turn that air conditioner on, and the refrigerant inside that compressor, around that compressor, is a liquid. Now you're going to be pushing that liquid through the compressor, and that's just going to damage the scroll coils and everything else. So we don't want to take that chance. We don't want to damage the compressor whatsoever. It's a common practice that we do. So I'm going to ask that you don't test air conditioners. And whatever number you want to choose is up to you. We're going to throw out a very conservative, safe number of 65 degrees. So like this time of year, and not until April probably, will we be testing air conditioners again. So, and we just have a standard disclaimer in our form. So determining the size of the compressor. Even though this isn't a real data plate that's up there, it was a real data plate. And what I did was I tried to pull all the numbers and everything else that's on there so we could do a little bit of decoding. All right. I know in the field, I usually tell people to look up buildingcenter.org. And I'm going to actually type that in the comments here. So you got it. So, and I'm pretty sure this is the right website. Buildingcenter.org. All right. And that's up there. So when you go there, what they did was they took every manufacturer and even the different years that the manufacturers did it, and they were able to decode all the different data plates that are on there. All right. But there's some things that you're going to have to kind of know so you can figure everything out. So in the model numbers, that's usually where they're going to hide the BTUs. And I shouldn't use the word hide, but that's where we're going to find how many BTUs this unit's going to be there. So you look for multiples of 12s or even 6s, because 6 is a half of a 12. So that would be a half ton. So if we go at the model number on this one, and I'm seeing TTX030. All right. So the 030 is going to basically tell me 30,000 BTUs. So at 30,000 BTUs, 12 times 2 is 24. 24 plus 6, which is a half a ton, gives me 30. So 2.5 tons is the size of this air conditioning unit. All right. Now, since we got the data plate up here, I'd like to go over a few other pieces of information that we can get out of this. All right. Now, I believe this is a train, the XL 1200. That's a train model out there. And they've been actually very good about typing the manufacturer's date in the upper right-hand corner of these data plates. So this one right here was manufactured August of 94. So that part's easy when we come through it. But if you go to that buildingcenter.org and you look up that data plate on there, or I should say that serial number, the J32210593, you know, and that I do, if I remember right, there was an actual serial number on there. It should show you how to decode that and come up with August of 94. But in this case, it was easy. All right. The next thing I want you to look for is the maximum breaker. Sometimes that's listed as maximum fuse that's on there. Now, in our company, we always take a photo of the data plate. All right. This is a big deal to us. We take a photo of the data plate, and when we go inside the electrical panel, now we have a reference that we can go back to. But where it says maximum fuse on there, that's the maximum fuse. We don't want to find one smaller than that either, all right? We should actually try to be somewhere as close as we can to that fuse without going over. So here they give you a recommended fuse or recommended breaker as well, and that's also 25 amps that's written on there. The HCFC 22, that they're talking about the refrigerant on there. The next number I want you to look at is the minimum ampacity. The minimum circuit ampacity is talking about the wire size, basically. So when this unit is running, I need to be able to allow 17 amps to flow through this system. So if I start doing my wire gauge measurements again, and what I should have committed to my memory, I know that a 14 gauge wire is only good for 15 amps. Well, this is telling me I need at least 17 amps. So that 14 gauge wire isn't going to cut the mustard. All right. The next size larger wire is going to be a 12 gauge wire. That 12 gauge wire is good for 20 amps. Okay, 20 amps is more than what this thing needs for its minimum amp. So I could put a 12 gauge wire and feed this air compressor unit or compressor cabinet unit. I could feed that with a 12 gauge wire. Then it says that the maximum fuse I could put on here is a 25 amp breaker. So even though a 12 gauge wire shouldn't have bigger than a 20 amp breaker, the manufacturer of this air conditioner is saying it's okay. And as long as the manufacturer says it's okay, it's okay. So in this situation, we could put a 12 gauge wire on a 25 amp breaker. That's not a problem. And if they want to go with a 10 gauge wire, they could do that too. You know, it's a little more expensive. It doesn't matter. You know, it's safer. But by all means, when the manufacturer of the air conditioner said this is the minimum, this is the cheapest you could go, and it still make it safe, well, then it's still considered safe in their eyes. All right, so off of this data plate, we know our maximum breaker. We know the wire size that it should be. We know how big our system is, and we're able to determine how old our system is too. All right, overfusing is okay. That's kind of what I was talking about beforehand. Not always are we going to be able to see the data plate, all right? Now, this rule of thumb is strictly that, just a rule of thumb when we come to this. And I'm going to go ahead. And clean up my board again. Let's go ahead and make that cheap little chart when I come to it. I gotta get a better eraser on my whiteboard. Alright. So basically, I like to have a little chart. I would strongly recommend that you get something like this so you can memorize these things. So if we write up on the left, amps. Let's find another one. And then we'll have copper. And then aluminum. And this little chart is actually something you should have with you all the time. Every time we look at an electrical panel, this is what we're going to end up with anyway. So for amperage, we're going to start with 15, 20, 30, we'll jump up to 50, 60, 100, 200. And then we draw some lines through all this. All right, so for a 15 amp, I'm going to need a 14 gauge copper wire or a number 12 aluminum. For 20 amps, I'm going to need a 12 or a 10. 30, I'm going to need a 10 or an 8. 50, I'm going to need an 8 or a 6. 6, 4, and then the NEC does say 4 for 100 amps. But I always like people to know number 3 in Chicago. All right. And it's typically a number 3 copper that we're going to run for there. Number 2 aluminum is a very common service drop in our area. And then the next one, you know, if you see a pattern, 14, 12, 12, 10, 10, 8, 8, 6, 6, 4, makes it for an easy way to remember this stuff. But for the next one, we're going to transpose these. And then, so we're going to go 2/0. And 4/0 if it was aluminum. So that's talking about a 2-aught wire and a 4-aught wire. So when we're dealing with the overfusing, and this again is all rule of thumb, that data plate that we saw before, that's our priority. This is not when it comes to it. All right. So let's say that I was feeding that air conditioning unit and I didn't have access to the data plate at all. So I'm feeding that air conditioner with a 10 gauge wire. What I'm going to do is take the next larger size wire, which is a number 8. Whatever breaker can protect that, that's what I can go ahead and use. So I'm going to go back to the slide drawing in a second, and that's at 125%. But if I had a number 10 copper wire on a 15 amp, or I'm sorry, on a 50 amp breaker to go ahead and protect everything. And let's see if I get back there. Good. So we got a 10 gauge wire coming across there. You can see our little fuses are marked at 50 amps. And that's part of that overcurrent. Now the reason they allow this is when the air conditioners start up, they use a lot of electricity. All right. There's that sudden surge of power that's going to come into this. And as that starts up, we don't want the breakers to trip because it's over. Now they're dedicated, nothing else is supposed to be attached to this. So it's just going to be the air conditioning. If that air compressor seizes up and it's not working right anymore, then it's going to be using a lot more than the 50 amps and it's going to go ahead and blow the fuse anyway. All right. So with air conditioning, I'm talking about central air conditioning systems. This is not acceptable for through wall units or window units or anything other than a central air conditioning compressor cabinet on the outside. And the overfusing is actually normal, and the reason is because of the sudden start. All right. This is just a little bit above and beyond what most home inspectors do, but I actually kind of like it a little bit. Let's see if I go back a couple slides. And we go back to this data plate here. Something that I didn't talk about was the rated load amps. So if you look at the bottom of that chart, you can see the compressor motor has rated load amps of 12 amps. The FLA stands for full load amps. Sometimes you'll see LRA, and that stands for locked rotor amps. All right. So full load amps is usually going to be the charge or the startup power that it's going to use. So this data plate is telling me when it starts up, it should be somewhere around 17.5 amps. After it's running, it should be running at somewhere around 12 amps. I take that plus the fan motor RLA, that gives me 13. So if you're going to go a little bit overboard, and I like to do this, all right, so if you're going to go a little bit overboard, we put amp meters on the power lines that comes through there when the air conditioner is running. And it should be somewhere between 60 and 90% of whatever the total of the RLA is, or the rated load amps. Now, for me, I know this is wrong, but it's just a nice, easy way for me to remember it. When I see the RLA, I like to think of it as running load amps. So after the system is running, these are the amperes that I'm supposed to be there. Now, I'm not supposed to be at max of that. If I get up that high, then my air compressor is struggling, and that usually indicates that I'm getting to the end of its lifespan. So I should be under 90% of whatever the total RLA is. So this time we had 13. So remove 1.3 out of that. So we'll go back down to 11 and a half, somewhere in that ballpark. I should be below that. If I'm over 12, then I'm going to start questioning things. And we could go ahead and just simply put that amp meter right around the wire, and then that's going to be able to read the current flow going through that wire.